Our final form for quadratic function is standard form, and this is when it's multiplied all the way out, there aren't any parentheses left. We have ax squared plus bx plus c. You may recognize this form from when we used our quadratic formula. Our essential question today is how do we graph and apply our knowledge of quadratic functions in standard form? Starting off by graphing. Standard form does not give us any information about how to put this equation onto a graph, so we have to use this form to find the information we need. We can tell from the leading coefficient, the a value. If it's positive, it will open up, as it does in our case. If it's negative, it will open down. To get the axis of symmetry, we use the equation x equals the opposite of b over 2a. This is a piece from the quadratic formula. We don't use the radical piece for this. In our case, b, the value being multiplied by x is 6, so we have the opposite of 6, divided by 2 times our leading coefficient, which was 1. Negative 6 divided by 2 is negative 3. So our axis of symmetry is x equals negative 3. To find the vertex, we substitute that back into the function for x. Make sure you use grouping symbols, especially when your x value is negative. If you're using a calculator to evaluate this, then you have to use those parentheses. Otherwise, your calculator will do order of operations that you don't want it to do. It will square the value and then multiply by a negative instead of multiplying negative 3 by itself. So we have 9 minus 18 is negative 9 plus 5 is negative 4. Our vertex x coordinate was negative 3, and we solved to get negative 4 for y. Our y-intercept occurs when we substitute 0 in for x. Notice what happens. Those first two terms both have an x value, so they go to 0. The y-intercept then is the c value, or the constant. If your function factors easily, you can also find the zeros. In our case, the factoring is t-chart, what multiplies to 5 and adds to 6. So we would get x plus 1 times x plus 5. If your leading coefficient is not 1, you might have to do the AC method, and you may not end up with integer zeros either. So you may not always want to find the zeros. You can get this graphed with just your vertex and your y-intercept. Setting each of those binomials equal to 0, we would get negative 1 and negative 5 for our zeros. Look at domain and range after we have it graphed. Plotting our vertex of negative 3, negative 4. Our y-intercept is 0, 5. And we did get zeros of negative 1 and negative 5. I will also flip that y-intercept across the axis of symmetry to get one more point, and creating a nice smooth U-shaped graph. Domain, it is a quadratic function, so we've got all real numbers. Range, it opens up, so y is greater than or equal to the y-coordinate of our vertex. Does our graph open up or down? Our leading coefficient is negative, so our graph will open down. To get our axis of symmetry, opposite of b over 2a. b in our case is negative 4, so the opposite of that is positive 4, divided by 2 times a. 4 divided by negative 4 is negative 1. Our axis of symmetry is x equals negative 1. So to get our vertex, we will substitute that negative 1 value back into the function for x. Solving for our y value, we have negative 2 times 1, or negative 2, plus 4, plus 7, which would give us 2 plus 7, or 9. So our vertex, we substituted negative 1 for x, solved and got 9 for y. The y-intercept is our c value, or the constant. The zeros in this case, we would have the AC method of factoring. What multiplies to negative 14 and adds to negative 4. There are no numbers that do that. So I'll show you how to graph a quadratic function when you only have 2 points. First of all, graph that vertex, -1, +9. Graph your y-intercept, 0, 7. And then use that axis of symmetry. This is a line across which the graph is symmetric to get a third point. Flip that y-intercept across the axis of symmetry. Now in this case, our graph isn't real accurate. We only had 3 points and they were quite close together, but it does give us an idea of what our quadratic function looks like. Domain, all real numbers. Range, it opens down, so we're less than or equal to the y-coordinate of our vertex.